In the last part of this lecture, I want to discuss another application of Markov chains, this time to a classification problem. Actually, this time it's not fully supervised learning, which we've discussed in the first part of this course. It's something called semi-supervised learning. So in this scenario, we imagine that we have data that we want to classify, but we have very few labeled examples. You can look at the example here that I'm showing, where each of these black dots corresponds to a covariate vector xi in R2. And we want to label each of these using a binary classification where it could be either the red class or the blue class. But we have an extreme case where we only have one labeled example of the red class and one labeled example of the blue class, and everything else is completely unlabeled. So if we wanted to learn a linear classifier like we've been discussing in the first part of this course, we would simply have these 2 points to learn the model on, and so we would perhaps learn a classifier that looks like this. The idea behind supervised learning, the idea behind semi-supervised learning is that we don't want to throw away the unlabeled data because that somehow gives us information about the structure of the data set. In this toy example, that structure is the rings, and so looking at this example, we might say that everything on the inner ring should be labeled blue, and everything in the outer ring should be labeled as the red class. Semi-supervised learning is the general approach to data modeling where we build a classifier. It's a classification problem or a regression problem where we use all of the information of the covariates in combination with this small set of labeled examples that we have. So we use all of the data in X and whatever Y's are available to us. So there are many ways that we can develop a semi-supervised classifier. I just want to look at the one example that relates to Markov chains. So in this case, the modeling motivation is to start a random walk at a particular point xi. So we're going to define a classifier where we take any particular point that we want to label. For example, we want to label xi. It doesn't have a label. And we start a random walk at that point. So the random walker at xi moves between the data points. So it moves from any point to any other data point according to a random walk that we have to define, but we start at the point xi that we want to label. We want to make the transition probabilities such that the probability of transitioning from any point to a nearby point is high, and the probability of transitioning from any point to a point that's far away is very low. So we start a random walk at the point xi. We then move from data point to data point according to this random walk, random transition matrix that we construct on the data set. And we continue to transition until we reach a labeled data point. Once we reach a labeled data point, the transitions terminate, the random walk terminates, and we define the label of the point xi to be the label of the point that the random walk started at xi terminated at. So let's look at one example of how we can construct the random walk matrix. For example, if we start at this point, we want to now have a transition matrix on every other point. So this is a zoom in of the previous slide. Imagine we have n total points in our data set. So we want to construct a transition matrix between this point and all n points, including itself. So there's going to be an n-dimensional probability transition distribution strictly starting from this point. So if there are n points, you can imagine that we have an n by n transition matrix where we construct the probability of transitioning from the ith data point to the jth data point by taking the Gaussian kernel between those 2 points. So that takes proximity into consideration. If b is small, then of course the probability of transitioning from this point to this point might be high if b is large enough to consider that close. but the probability of transitioning from this point to this point, or this point to this point, or any other point outside of the range defined by B, that transition probability will be very, very small, essentially 0. So we construct the Gaussian kernel between all the data points. It's an n by n kernel. We then normalize each row of that kernel matrix so that we have a probability transition matrix. So we have the Gaussian kernel between all the points. We normalize the rows of that kernel matrix so that we can now have a Markov transition matrix. Finally, and crucially, if the ith data point is labeled, we then redefine the transition for the ith data point to be a self-transition with probability 1. So if xi has a label, no matter what the label is, we look at the ith row of the transition matrix, we set everything to 0, and then we set the self-transition probability to be equal to 1. So all the labeled data will transition to itself for all of infinity. It'll, with probability 1, always transition back to itself. And so that's how we can now terminate the walk. Once we start at an unlabeled data point and we walk, around along this data set, we finally hit the red point, and now we simply stay at the red point because we'll have a self-transition with probability 1. So that's how we terminate. What we've done in the language of Markov chains is we've created an absorbing state. So imagine that we have S states. We'll become a little more abstract now. If the probability of transitioning from the ith state back to the ith state, so if we're at state I at time t minus 1, and the probability of a self-transition, so that we're at state I at time t, if that's equal to 1, so if the probability of a self-transition is equal to 1, then we say that the ith state is an absorbing state, since we can never leave it. It's like a black hole. So the question now is, for this modeling problem, and in general, in fact, this is a general result, given an initial state, S0 is equal to J. So given that I start in the jth state, given a set of absorbing states with the index I1 through Ik, so imagine we have k absorbing states, and these are their indices, and also given a Markov transition matrix, M, what is the probability that the Markov chain terminates at any of these particular absorbing states, given that we've started at state J? So what we're looking for is a k-dimensional probability distribution that says the probability of terminating at any one of these different absorbing states, given that I start in state J. Can we calculate that? So now if we can calculate this probability for this general Markov problem, we've solved our semi-supervised classifier problem, because this, in the language of our semi-supervised classifier, this probability is the probability of starting at a point xj that's unlabeled and terminating at one of the k different labeled points. And then we just take their corresponding labels, and if we want to know what's the probability of terminating at a point with label 1, we sum the probabilities of terminating at any point with a label 1. So the answer to this problem, or at least the first way to approach it, is to simply start a random walk at state J and keep track of the distributions on states as a function of time. So we start the random walk deterministically at state J at time 0, and so that in that case W0, using the same notation previously, is a vector of all zeros. It's a vector of with n minus 1 zeros and a 1 in entry J. So W0 is going to be an n-dimensional vector, if we have n data points for our problem, with a 1 in the jth dimension and a 0 everywhere else, because we know where we're starting. So in this case, it would be s-dimensional. Then if M is the transition matrix, it could be any transition matrix, we already know that the probability of where I'm at time t plus 1 is equal to the probability of where I'm at time t times M. And so therefore, what we want is we want W infinity which is equal to W0 times M infinity. And actually, because this Markov chain does not satisfy the conditions that we had previously, meaning that given that we start at any state, we can reach any other state. That's not true, because now given we start at a terminal state, at an absorbing state, we cannot ever leave that state and reach any other state. So the stationary distribution in this case is not going to be the same for all starting points. So if we wanted to be more clear, we could simply say superscript j here says where the 1 is, what the starting state is, and then that's going to lead to a final distribution that is dependent on the starting state. Okay, so let's try to calculate now what's the probability distribution on terminating at any given absorbing state, given that I start at a particular state. Towards this end, let's rewrite the Markov transition matrix in a way that's going to be much more convenient. So let's group the absorbing states at the bottom and the non-absorbing states at the top. In that case, we can write the Markov transition matrix this way. So if we imagine that we have k absorbing states, then the bottom k rows of this transition matrix will have a 0 in this portion and a k-dimensional identity in this portion. So if we have s different states and we have k absorbing states, this 0 will be a k by s minus k matrix, all zeros. And then this final k by k matrix will be the identity. That's going to model the fact that we have a self-transition with probability 1. So given that I'm in one of these bottom k states, the probability of self-transitioning is equal to 1, according to this construction. And now let's break up the top half, which is going to be s minus k rows and s columns, according to the same way that we broke up the bottom half. So B is now going to be a k by k dimensional matrix. I'm sorry, it's going to be an s minus k by k dimensional matrix. A is going to be an s minus k by s minus k square matrix. So A says the probability of transitioning from a non-absorbing state to another non-absorbing state, and B has the probability of transitioning from any non-absorbing state to any of the absorbing states. So if we make a transition from any of these top rows to a state indexed by B, then we transition to an absorbing state, and our Markov chain is going to essentially terminate there. Okay, so we make this simplifying assumption. Now we, again, write the observation that the distribution of where I'm at time t plus 1 can be broken down to the distribution of where I'm at time 0 times the matrix M to the power t plus 1. And so this is the matrix M multiplied by itself t plus 1 times. And remember, W0 is a vector of all zeros except for a 1 in the index of the state that I'm starting at. So that tells me where I'm going to end up at, where I'm going to be at time t plus 1. And now we want to know what happens as t goes to infinity. So in order to understand what happens when t goes to infinity here, we really need to understand what happens when t goes to infinity here. So we want to know what's going on with this matrix M to the power t. So let's inductively figure this out by looking at the first two cases. So M squared is equal to this matrix times itself. And so we have AB times A0 is A squared. AB times BI is AB times plus B. And then 0I times A0 is 0. And 0I times BI is just I. So here we've done the same sort of rules when these are scalars. The same exact logic follows when these are submatrices as well. Okay, so we've calculated for M squared. Let's now look at M cubed. So M cubed is this times itself 3 times. We already know what M squared is, so we'll take this and put it in here. So that's figuring out the M squared portion. And then we just multiply it by itself again to find M cubed. Okay, so we have AB times A squared 0, that's A cubed. AB times this term, so A times this term plus B times this term. We have a B here. And then we have A times this term, so we have A squared B plus A times B plus B. 0 times A squared plus I times 0 is 0. And 0 times this term plus I times I is I. Okay, so we've already now started to uncover a pattern, which we're going to return to in a second. But first I want to take a one-slide digression about the geometric series. So what we're going to see is this is an example of a matrix version of the geometric series. So let's look at the scalar version of a geometric series first, and then we can see the relationship to the matrix version. So let's let R be any number between 0 and 1. And now we want to calculate the sum of R to the u, where u is 0 to t minus 1. So we take R, we raise it to the power u. We do that for u equals 0 to t minus 1, and we sum all of those up. We can show that this sum, which is a geometric series, is equal to 1 minus r raised to whatever this top thing is plus 1. So since we have t minus 1, we raise it to t. And then the denominator in all cases is simply 1 minus r. So no matter what t is here, we have 1 minus r in the denominator, and then in the numerator we raise r to the power equal to 1 plus this top number. And so if we let t go to infinity, since r is between 0 and 1, r to the infinity is equal to 0. And so we simply have 1 divided by 1 minus r is the limit of the geometric series. So how can we prove this? It's very simple, very straightforward, and very clever. So if we let ct be equal to this sum of r to the 0, which is 1, plus r to the 1, which is r, plus r to the 2, up to r to the t plus 1. So we're letting this term be equal to c subscript t. We want to know what's c subscript t. So we want to know what is this value. Call it c subscript t. And now let's take the left and the right-hand side and multiply it by r. So r times c subscript t is equal to this numerator times r. And so we simply shift everything. 1 times r is r, so let's just write it underneath r. R times r is r squared, so let's write that underneath r squared. But then down here, up here, we have rt plus 1 times r. That's rt, and so we have this term here. So we've simply taken the numerator and multiplied it both sides by r. Now let's take this top part and subtract this bottom part. So this minus this is therefore equal to this minus this. And so we have ct minus r times ct here. And notice that we get cancellations in this case. So this is the cleverness of this thing. So we have 1, which doesn't have anything here, but everything in between cancels. So we have 1 minus r to the t. And now we solve for ct, which is what we cared about to begin with. We define that to be this sum. When we solve for ct, we get what we want. When we let t go to infinity, we get the limiting case. Okay, so returning now to the absorbing state problem, we've seen the pattern from the previous slide. What we can show is that the pattern is as follows, that m to the t is equal to the matrix A to the t. Down here we always have a 0 and we always have the identity. And then up here we have B times the sum of the matrix A to the u, where u ranges from 0 to t minus 1. So we have this sum. If you want to go back, we can see that for 3 we simply bring out the matrix B and multiply by the sum of a squared plus a plus the identity matrix. And so in general, if we raise it to the power t, we have this term. If t equals 3, then we have two terms. We have a squared plus a plus identity. So the matrix A raised to the power 0 is the identity matrix. Okay, so now we have two things that we can show. First, we have to show, we won't prove it here, but we can show that as t goes to infinity, the matrix A raised to the power t, infinity, is equal to 0. So the limiting case, the limit of this thing as t goes to infinity is equal to the matrix of all zeros. And then finally, here's the matrix form of the geometric series. As t goes to infinity, we have that this sum is equal to the identity matrix minus A inverse. So notice here we had, because we were working with scalars, r was a scalar, we had 1 divided by 1 minus r. The matrix form of that is the identity matrix. 1 becomes the identity matrix minus A, and notationally we can't say 1 divided by a matrix. Notationally we have to take the inverse. So this is the corresponding matrix version of 1 divided by a scalar is the inverse matrix. Okay, so we can plug in, what we care about is the infinite limit, so we plug in 0 here, we plug in this term here, and then we find that after an infinite number of steps, starting from a particular state encoded in the vector w0, where I end up at in an infinite number of steps is equal to w0 times this matrix of zeros here. I have this term here in the upper part, and I have the identity down here. And so what this vector matrix product is doing, because remember, w0 is a vector of zeros, except for 1 in the state corresponding to where I start. What this vector is really doing is simply picking out a row of this matrix, because I'm never going to start at a terminal, at an absorbing state, so I'm not going to start here. I'm going to start at one of the s minus k non-absorbing states. And so I'm literally just picking out a row of this matrix. And so I'm picking out the probability of which of the absorbing states I terminate at. And so, for example, in returning to the semi-supervised classification problem, given that I start at point xj, the probability that I terminate at the ith absorbing state is simply equal to the jith element of this matrix, which I can calculate, because A and B are submatrices of my random walk matrix that I constructed using the kernel. So let's look at an example. Here's our data set. The black points are unlabeled. The blue and the red point are the two labels that I have. We constructed a Gaussian kernel with a good kernel width, so this was tailored to this problem. And we see that and we color code each point based on the label that we end at. So this point here is color coded red, almost perfectly red. We have an average between red and blue, except it's almost entirely red, because with probability almost 1, a random walk started here is going to end up at this red point. So we don't know how many steps it's going to take. It might take 1,000 steps just moving around back and forth down here, but eventually it's going to hit this point, this labeled point, with probability very close to 1, which is why it's labeled red. Similarly, for any point started in this region with probability essentially 1, a random walk started at any of those points is going to terminate at a blue point. So what we're saying here is that we've tuned the kernel width such that the probability of jumping over this chasm is 0. And so of course that means this method's very sensitive to that setting. If we increase the kernel width, then we get something that looks like this. So I don't know how it shows up on your screen, but this is essentially purple because we have an average between red and blue here. So we get something that transitions from strongly red to purple here, which is saying that given that I start here with 50% chance, I end up making it here, and with 50% chance, I end up jumping this gap and ending at this blue point here. If I start at the inner part, I have a much easier time making a direct line to the blue label point, so I don't jump out this way with as much likelihood. So this, I show this slide to give you a sense that it is something that's sensitive to parameter setting. For a toy example like this, we can look and see what the proper setting is, but in practice, you won't necessarily know what the manifold looks like. You won't know what these contours look like. So things like cross-validation or kernel parameter learning techniques would be necessary for that case.